In the field of medical artificial intelligence, researchers have developed a new model called OmniV-Med, designed to handle a wide range of visual data types like 2D images, 3D scans, and videos, all while integrating textual instructions. This approach aims to create a universal system for medical understanding, addressing the limitations of existing models that often use separate components for different types of data. The paper, titled OmniV-Med, Scaling Medical Vision Language Model for Universal Visual Understanding, is authored by a team from Zhejiang University, Alibaba Group, and the University of Illinois at Urbana-Champaign. They highlight three main technical contributions that make this model stand out. First, they built a comprehensive dataset called OmniV-Med-Instruct. This dataset includes 252,000 instructional samples, covering 14 different medical image modalities, such as X-rays, MRIs, CT scans, and pathology slides, and 11 clinical tasks. These tasks range from diagnosing diseases to analyzing surgical videos. By compiling this diverse dataset, the researchers provide a robust foundation for training models to handle real-world medical scenarios, which is crucial because medical data is often fragmented and specialized. Second, they introduced a rotary position adaptive encoder. This is a key innovation that allows the model to process multi-resolution 2D and 3D images, as well as videos, all within a single unified architecture. Unlike traditional models that rely on fixed positional embeddings from encoders like clipbit, this new encoder adapts dynamically to varying spatial structures and temporal dynamics. For example, it can handle the high-resolution details of a gigapixel pathology slide or the sequential frames in a medical video without needing separate encoders for each modality. This adaptability helps in aligning representations across different data types, making the model more efficient and versatile. Third, they developed a medical-aware token pruning mechanism. In medical imaging, especially with volumetric data like CT scans or videos from surgeries, there's often redundancy, such as similar consecutive slices or frames that don't add new information. This mechanism identifies and removes about 60% of the visual tokens while preserving performance. By exploiting this spatial and temporal redundancy, the model reduces computational demands without losing accuracy, which is particularly useful for processing large datasets or running on limited hardware. The researchers evaluated OmniV-Med through empirical tests on 7 benchmarks, covering 2D images, 3D imaging, and video understanding. Their largest model, OmniV-Med-7B, achieved state-of-the-art results compared to previous methods. For instance, on the VQA-RAD dataset for radiology question answering, it outperformed LLAVA-Med by 5.4% in open-ended questions and 7.6% in closed-ended ones. Similarly, for 3D tasks, it surpassed M3D-Lamed by 4.4% on closed questions and 9.7% on open ones. In video benchmarks like COLIC 80 VQA for surgical videos, it improved by 16.9% over surgical LLAVA. A notable aspect is the lightweight version, OmniV-Med 1.5B, which delivers comparable performance but is much more efficient. It can be trained on just 8 RTX 3090 GPUs and supports fast inference on long videos, making it practical for clinical settings where resources might be limited. This work addresses several challenges in the medical domain. For one, there's a lack of encoders specifically designed for 3D volumetric data and temporal videos, and existing general models struggle with the unique characteristics of medical visuals, like varying resolutions and the need for fine-grained details. OmniV-Med overcomes this by providing a holistic framework that integrates these elements with textual data, paving the way for applications in eye-assisted surgery, adaptive treatment planning, and beyond. The model's ability to process diverse inputs seamlessly could revolutionize how healthcare professionals interact with AI, allowing for more integrated and efficient diagnostic tools. The researchers plan to release the data, code, and models to the public, fostering further advancements in the field.